Hey, I'm just making a video on the group problem that we did not cover that well in class because it's easier for me and saves me a bit more time than just writing everything out. So, first of all, I did not like this diagram. It's way too complicated. Too many terms. This. Whatever this stuff is completely unnecessary. So, let's axe all that. All this, all this above diagram is trying to convey is that you have some object, this package, orbiting around this planet at some velocity v naught. And in this initial state, initial over here, has a velocity v naught that makes an angle theta. With this, that makes an angle theta relative to this radial axis that stems from this planet. And based on the above diagram, we also have a coordinate system. We're using cylindrical coordinates. So we have a unit radius vector, a unit k-hat vector, and just as an extra aside, with these two vectors defined, you can actually, by right-hand rule, determine that theta hat must point upwards, or maybe like this, or this. You just saw that by right-hand rule, when you cross r hat and theta hat, you get k hat pointing backwards, always. So, with that, all that set up, problem A, because problem A was way too unnecessarily confusing. Is there a point about which angular momentum is constant? What this is trying to basically say is that since we learned in lecture that angular momentum is defined with respect to a pivot, we need some axis of rotation to analyze how much momentum we have. It's essentially saying, where do I place S? Where do I place S, the pivot, such that the only force that's being active here, F of G, exhibits no torque? And you may remember that torque is defined as R cross F, which is 0 if R is parallel to F. So, since we know that gravity is the only relevant force here, on acting on the package, F of G, we can technically place the pivot as anywhere. It can be here, it can be here, it can be here. But if we place it here, your R vector will be pointing from this pivot to the package, and clearly, my bad, clearly, this vector, they are not parallel. So the cross vector is non-zero. That doesn't work out. There's going to be torque changes. So maybe we can do it here. If we place it like this, you have an R vector spanning all the way over there. F of G points horizontally. It's parallel in that time period, but it's saying when angular momentum is constant, that implies that angular momentum cannot be changing with respect to time. If this package moves a little bit in time, it's going to move over here. Your new gravity will be pointing inwards towards this planet again, but your R vector is now no longer parallel with F of G. So this pivot doesn't work out as well. However, if we define S to be at the core of the planet that's attracting this package towards it, then no matter where the package is, your radial vector pointing from S to the package will always be aligned with the gravitational force of the package going towards the planet. No matter if it's at the initial state, if it's in some intermediary state, your R vector is always going to be pointing like this. Your gravity is going to be pointing back in this direction in return. And even at its final state, when it's just barely grazing the planet, it's still going to be parallel. So this point at the core of the planet is the point they're trying to tell you to look for. It was just annoying in class because they already drew it on the diagram at the start. So they gave you the answer basically before they even ask you a question. I don't know what's up with these people, but okay. So S is at planet core. Okay. Is the energy constant? Only criterion is that no non-conservative forces. I cannot spell. Non-conservative means that you cannot define the potential energy diagram, uh, a potential energy for the force, and it's path dependent. In this diagram, yep, my bad for the pauses, I'm not used to recording. In this diagram, the only force we have acting on the package is gravity. And gravity, as we all know, you can define the potential energy like so. So, all forces are conservative, which implies energy is also conserved. And I say also because if we put our pivot S at the planet core, that means angular momentum is constant. So both energy, let's leave that as one, and angular momentum, L, is conserved. Nice. So we can write an equation for the energy balance and an equation for the angular momentum balance of the package as it's tracing its path towards the planet. So part C is finally asking, for what angle theta will the package just graze the surface of the planet? Well, since we have two conservation equations, we can pick out the initial final state to compare between between these two. So we already drew out the initial state. Let's copy this diagram. If I can select it. There we go. I have my practice solving down below. Don't worry about that. Let's hide it. Cool. Maybe I should drag this down a little bit. There we go. So that's the initial state on the left here. Final state. We can imagine a path like this. And then we have the package over here, just barely grazing the planet's surface. So if Notability wants to be a friend today, the package will have a final velocity v of f, and that's all in the theta hat direction. Because it's barely grazing the surface of the planet, just graze. It shouldn't be going any further into the planet, or it shouldn't be going any further out of the planet at this instant. So that's all fine and dandy. Now it's time to write out the two conservation equations. We have initial, final. Or I should organize this a bit better. Energy balance. Your total energy at the initial state should equal to total energy at the final state. The two energy types we have is gravitational and kinetic since it has a starting velocity. Gravitational potential energy is negative g, the mass of the package, and the mass of the planet over the radial distance away from the planet core, which is 5 rp. 5 rp plus. In this reference frame, the planet is not moving, so we can ignore the planet for now. The package is moving though, with total velocity v naught. And since kinetic energy only really cares about the total velocity, we write 1/2 mi v naught squared. And that is equal to the final energy state at this point, since we know that energy is conserved, it's also gravitational potential energy. It's still a bit away from the core of the planet, and it has an even greater final velocity because it's getting closer to the planet. So GMI MP over RP, since now it's only a planet radius away from the core, plus the usual kinetic energy VF squared. From here, we can cancel out some terms. Doot, doot, doot. Nice. So let's just save this real quick. We can go on to angular momentum. Angular momentum. Momentum. The angular momentum at the start is equal to the angular momentum at the finish. And remember that angular momentum is a vector quantity, just because in 3D things can get complicated. So angular momentum at the start, we have R initial plus the P initial, where P and R are both the vector quantities describing this object. R is the vector spanning from the planet core to the package at this initial state, and P of I is when you calculate momentum of the package using this initial velocity. And this is equal to R final plus P final. And if we expand these two out, in this coordinate system, we have the displacement vector from the pivot is 5 RP R hat crossed with I V naught. And since this is the cross product, I'm actually going to rewrite this as isolating the perpendicular component of this, since we know that only the perpendicular components of these two vectors actually interact with one another. Well, okay, that phrasing is a little bit ambiguous, but I'm trying to say that only this component velocity, only this component interacts with the displacement vector from the pivot. So to actually get that by trigonometry, this is V naught sine theta. Is that right? Yeah, that's right. Okay. So the perpendicular component of that is mi V naught sine theta in the theta hat direction. And that is equal to or PR in the final state over here. And keep in mind that the final velocity state is fully in the theta hat direction just by the grazing condition. So cost with MIVF theta hat. And since R hat cross theta hat is equal to Z hat, we have, well, we can cancel out some terms here first. So let's cancel out the RPs. We can also cancel out the VIs, but damn i's. Then we get 5 V naught sine theta Z hat is equal to VF Z hat. This implies that the components, these two are equal. Sine theta is equal to VF. This is equation 2 that we can sub into this. And now it's just a bunch of algebra. Awesome. Cool. Isn't algebra fun? You start learning in middle school and then suddenly you just get hit with all this stuff Maybe we could go back, but math isn't that interesting back then, so maybe not. E over RP plus 1 half VF squared. And what we're trying to actually solve for is theta. So we need to substitute that in to here, which is very, very neat. But first, we're going to move this over to the left-hand side and multiply everything by 2. So we get 4GMP over 5RP plus 1 half V naught squared. And since I just said we were going to multiply everything by 2, let's actually do that. AGMP over 5RP plus V naught squared is equal to VF squared. And now let's substitute this in. We get is equal to 5 V naught sine theta squared. More algebra. I love algebra. This one of 25 terms comes from squaring this and dividing both sides. And that's equal to V naught squared sine squared theta. We can knock this out by dividing these terms. This is 1. The V naught squared gets added to the bottom there, and V naught squared disappears from the right-hand side. Then we can finally isolate what sine is. Sine theta is equal to square root of this entire thing. So that's 1 over 5, parentheses, 1 plus AG and P over 5RP V naught squared to the 1 half. Finally, you got the answer the slideshow should have if I did my algebra right. Of sine of 1 over 5 square root of 1 plus 8GMP over 5RP V naught squared. Man, what a great problem. If we compare this solution, just to check, that is indeed, it looks like what they got. So good job, team.